So good evening everyone. So in this lecture we we maximize we maximally try to finish the our topic law of mass Hall effect we have discussed. So in the new chapter we have to discuss what is the our semiconductor diodes we have. Okay. So we have know that the PN junction diode, channel diode, tunnel diode, LED, pin and avalanche photodiode. These are the semiconductor diode. So in PN junction diode, a semiconductor diode is a so we have to discuss what is PN junction diode. So in PN junction, a semiconductor diode is a polarity sensitive two terminals in which P and N junction are formed. Okay, between P semiconductor material and N semiconductor material, we have discussed in chapter 8. N-type semiconductor is formed by the introducing the pentavalent dopant, while the P is due to the form by tetravalent dopant. Okay. Also, in the N-type semiconductor, electrons are majority. So in P-type, P mean electron are majority. Okay. So N-type semiconductor, N-type and negative. So electron is majority, while hole are the minority carriers. Okay. Whereas in P-type semiconductor, holes are the majority carriers. In P-type, holes and the electron are the minority carriers. So a PN junction is formed by introducing the donor impurities on one side and donor impurities on one side and the acceptor impurities on the other side. Okay. Other side of the crystal. Okay. So the arrow is associated from the P region to P region and vertical line to the N region. Okay. So PN region are referred as the anode and cathode respectively. So silicon germanium most commonly used for fabricating the semiconductor diode. Okay. The electron in the N region and the hole electron in the N region and the hole in the P region combine near the junction, as a result forming a region near to the junction to devoid the free electrons and holes. Okay. This region is uncovered. Positive and negative holes are called depletion region. So when we have to explain what is depletion region, so how we explain? So as we know that the electron present in the N region and the holes present in the P region combine near a junction, resulting a region near to the junction and that are devoid of free electrons and hole. When devoid of free electrons and hole, this region of uncovered positive and negative ion is called depletion region. Okay. Due to the depletion of free carrier in this region, the thickness of this region is due to the depletion of free carrier in this region. The thickness of this region is on order of 0.5 microohms. Okay, micrometers. Electron is the majority carrier in the N region and negatively charged ion in the electron is the majority in the N region and the negatively charged ion in the P region. Near the junction repel each other. Okay. Similarly, the holes in the P region and the positively charged in the N region are repel each other. So an effective potential of the order of few tenth of the volt is called contact potential, barrier potential, and it develops across the depletion region. And however, some of the holes and electrons have a mm, sufficient kinetic energy. So sufficient kinetic energy to overcome the contact potential and able to pass through the depletion region. Okay. And this result is in the flow of N region to P region and the flow of holes in the P region. This constitute the majority carrier flow vector. Okay. So we see that the P region and the N region. So it's a simple of the PN diode. We can simply like this one PN diode. Okay. So although also hole is a minority carrier are present in the depletion region, and the N region pass to the P region. Okay. So this is the so how can we say? So this constitute a minority carrier flow vector and the relative magnitude of the minority and the majority flow vector and as such that the net flow in this either direction is zero. So this refer to the open circuit condition of the semiconductor diode where no bias voltage is applied. So where no bias voltage applied to the diode. In another word, we can say that in absence of applied voltage, the net flow of current in the semiconductor. So we can say that in another word, in the absence of applied bias voltage, the net flow in the current in the semiconductor diode become zero. Okay, and this shows that the PN junction with no applied bias. Okay, you can see that no biasing depletion region created. So PN junction has no applied voltage. So in subsequent paragraph, we discuss the response of semiconductor hole in forward bias. Okay. What is forward bias condition? How we explain the forward bias condition? In semiconductor diode is a forward bias by applying the positive potential on the P side. Okay, on the whole side we applied forward P to the positive potential. Okay, and negative to the N side region, and this applied potential cause an electron in the N region and hole in the P region combined with the positive and negative ion respectively in the depletion region. Okay, this result in the reduction of the depletion width. Okay, and the decrease in the potential barrier in the junction. Okay, as the applied bias is increased the magnitude as the applied bias is increased in a magnitude, the width of the depletion region decreases till at the point to reach to the star price of the number of majority carrier crosses the junction. Okay, till depleted and the majority carrier crosses the junction. In other words, a large number of holes crosses the junction of the P to the N region. So we can see that the whole large number of P crosses the junction of depletion region inside the N region, and a large number of electrons crosses the junction in reverse direction. And this is the form and this and they form the N region to P region. Okay, it may be mentioned here that a hole traveling from the left to right. So left to right constitute a current in the same direction. Okay, this result in exponential rise in the current due to the majority carriers. Okay, and the current due to the majority carrier is referred to the forward current and is in the range of few of the milliampere. Okay, and typically the voltage across for a forward bias diode is less than. So typically the voltage across the forward bias voltage is less than 1 volt. Okay, and depend upon the diode material. For example, a forward voltage in a silicon and germanium is typically 0.7 and 0.3. So in silicon we can see that 0.7 volt, and germanium is 3.3 volt. Okay, holes when we applied positives to the P side and negative this one. So holes, we can see that the holes flow from the region, and the depletion which decreases as we apply the positive potential at the P side. The majority carrier on the P side passes the depletion result to the N side and exchange their action. So holes flow in direction, electrons flow in a depletion region decreases. Okay, so the flow of minority carrier remain the same as in the flow of diode, no applied voltage, and the current contributed by the minority carrier is referred to be reverse saturation current to reverse leakage current, and in order of few of the nanoampere or few microampere. Okay, the reverse saturation current is in the opposite direction to the forward current. However, it is a magnitude negligible as compared to the forward current. The voltage VI characteristic of the diode discussed in the 9.3 section. What is reverse bias condition? So reverse bias condition, diode is said to be reverse bias condition when the external potential across it such that the positive terminal is connected to the N region. Positive terminal is connected to the N region and the negative terminal is connected to the P region. Okay. This result in the widening depletion region as the electron and hole pair are drawn away from the in which electrons and holes pair are drawn away from the junction due to the polarity of the applied voltage. Okay, the widening of depletion region reduce the flow of majority carrier to the approximately zero. Okay, in which we see that the holes flow because the negative potential is applied this one, so holes flow in this direction. Okay, and the in positive voltage applied, so electrons flow in that direction. So the depletion region which increases. Okay, depletion region which is increases, and the minority carrier flow remain the same in the case of diode, no voltage applied. So the reverse saturation current does not significantly change in the reverse bias potential. Okay, so however, so where we are, however, it is a strong function. So we see reverse bias condition and forward bias condition. So ideal and practical diodes. So what is ideal diode? So ideal diodes behave like a switch. Okay, so, so actually ideal diode behave like a switch that conduct current only in one direction from the anode to cathode. Okay, A to C. Okay, and the ideal diode act as a short circuit when the forward act as a short circuit when the forward bias as the open circuit short circuit in the forward bias and open circuit in the reverse bias condition. Thus, the resistance of the forward bias condition and the forward biased diode is zero, and the resistance of the forward bias is zero, and the resistance of the reverse bias condition is infinite, as shown in the figure. So resistance increases. Okay, zero, zero, and infinite. Okay, this line representing the resistance. Okay, so what is ideal and what is the practical? The actual diode differ from the ideal diode described in the in forward bias condition. The ideal diode act as a closed, but the act as closed switch with zero on resistance that allow the current to flow in one direction and from the anode to cathode. However, in the practical diode do not conduct until a certain value of forward voltage is applied then. Okay, so as we know that the in forward 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 bias condition in which and our circuit behave that part behave like a short circuit. Okay, but in a practical condition it does not conduct until a certain value of the forward bias voltage is applied. Then this voltage is referred as a cutoff or a knee voltage or threshold voltage is the order of less than one or the less than one for the semiconductor. Okay, also the on resistance of the practical also on resistance for the practical diode, it is not zero and varies from few ohm to few hundred ohms. Okay, In the reverse bias state, the practical diode differ from the in the reverse bias state, the practical diode differ from the ideal open switch as is the condition is small. Okay. Also the sharp increase in the reverse current when the applied reverse bias voltage exceeded the reverse breakdown voltage. Okay. so so sorry. So what is VT? VI, voltage ampere characteristic of the VI graph of the diode. Okay. So VI as referred to the voltage ampere characteristic of the semiconductor, both forward and the reverse bias condition expressed by the following universal diode equation referred as a Shockley diode. Okay. So in which we have to say this ID current is equal to I naught e the power V. So how can we learn ID is equal to, so we have to write like id, how we write, so id is equal to I naught. Okay, and e the power vd by eta vt minus 1. Okay, where vd is the voltage across the vd is the voltage across diode, and id is the diode current, and I naught is the reverse saturation current, and eta 1 is for the germanium and silicon. Okay, for silicon it is 2, for germanium eta is equal to 1. So id is equal to I naught e the power vd by n eta vt minus 1. Okay, so this is the argument where we have discussed the vt. Vt is the volt voltage equivalent for the temperature. Okay, volt equivalent of the temperature. So vt is equal to kt by q. So k is, as we know, k is a Boltzmann constant, approx 6.6 into 8.6 into 10 to the power 5 in this one, 8.6 into 10 to the power 5 into the electron volt. Q is the electron charge and K is the temperature. Okay, so diode voltage and the diode current as a positive, this one. So VI is the characteristic of the PN junction diode, generally as evident for the figure. When diode is in forward bias condition, the minimum voltage that must exceeded before the sufficient. So V, for the forward bias condition, we require minimum for VD to exceed before the sufficient conduction of the current through the diode. Okay, in another word, we can say the current flow through the diode when it's in forward bias, and when the applied voltage is greater than the cutoff voltage, this one. The cutoff voltage is ranging from 0.7 in the case for the silicon, and 0.3 for the germanium. Okay, when the applied voltage exceeded the cutoff voltage, there is a sharp rise in the current through the diode. Okay, in other we can say that a very small increment in the there is small increment in the voltage Vd result in very large changes in. So increase for a very positive, this one. So in reverse bias condition, a peaky voltage. So we can see that we can see. So when we applied the forward voltage, and the cutoff will sharp rise in current through this one. Okay, for the positive value of Vd, the first term of the equation will grow exponentially over the power effect the term, and the first term corresponding to the current voltage through the diode, and second term corresponding to saturation current. Thus, the current through the diode varies exponentially with the applied voltage. Okay, and provide that the applied voltage is greater than the cutoff voltage. The forward current is measured in milliampere. In reverse bias condition, the small current that flow in a reverse saturation current, and it is the order of few of the nano amperes. Okay, it is this current is independent of the applied voltage. The semiconductor break the voltage reverse breakdown and the peak inverse voltage. This voltage junction is sudden rise in the current, okay, due to the damping in the diode. Hence, the diode are operated in the reverse bias mode, and their operation voltage should be less than the breakdown voltage. Some of the diode known as breakdown diode and designed to operate the breakdown. Right. So the what is the VI diagram? VI diagram is equal to this one. So after a certain limit, after certain cutoff, it got rise, and after the damping effect inside the diode, the reverse saturation current and the reverse background voltage is this one. Okay. The temperature of VI characteristic. So temperature has significantly affect the VI characteristic. Okay, as efficient evident, we can see that the reverse bias voltage cut off in a voltage function. So we can see that as we increases the temperature, the cutoff voltage also decreases. So temperature dependence of the VI characteristic. So as the temperature increases, decreases, as the temperature is decreases, the reverse voltage, reverse breakdown voltage also decreases. Okay, as the temperature increases, the cutoff voltage for that in uh, cutoff voltage for the forward bias condition also decreases. Okay, so we can say the formula of current is equal to I naught as is equal to I is equal to in function to the power t minus t1 by 10. Okay, so dv by dt is equal to reverse bias voltage decreases with increase in temperature, and when the cutoff in voltage for forward bias condition, that for which the current decreases with the increase in temperature. So current decreases as decreases with increase in temperature, and the cut up in voltage forwards with the temperature. This one. What diode resistance, static resistance, this one dynamic resistance. Okay. Average AC resistance is equal to D2 minus this one. Diode junction capacitance. So transition capacitance. Okay. So after that diode equivalent circuit. Um, in load analysis in the diode circuit, so we don't need that much of detail. Breakdown diode, what is this? Avalanche diode. So in avalanche diode, we in this case the avalanche diode, one application is reverse bias. The thermally generated carrier has sufficient energy to disrupt the covalent bond, thereby resulting in the free electrons. They are free. So in case of avalanche diode, an application of reverse bias voltage. Okay, reverse bias voltage, the thermally generated carrier has sufficient energy to disrupt the covalent. So in the avalanche application of reverse bias voltage, the thermally generated carrier has significantly energy to disrupt the covalent bond, hereby resulting in the free electrons, and these free electrons the knock out knock out more electrons from the adjacent bonds, and the process is regenerating and referred to the avalanche multiplication. Okay. So avalanche in which we can see that at a thermally generated carrier has significant energy and can high kinetic energy and disrupt the another covalent. Is the avalanche multiplication. Avalanche breakdown mechanism is a predominant in the lightly doped diode in which broad depletion region. Okay. So Zener diode, breakdown phenomena. The breakdown phenomena in the case of Zener diode is a result in electron breaking their covalent bond due to the intense strong electric field at the junction. Okay. The breakdown phenomenon in the Zener diode it result in the breakdown of the covalent bond due to the extensive मोको मोको 25 मिनट डाटा यूज कर रहा था मैं क्या? सिम चल रहा मैंने सिम बंद है ना बदल के बात है बजरंग दल वाला चल रहा है इतना बेल 2.2 ये सब में तुम्हारा है थंबनेल कहाँ से लाया भाई थंबनेल हम बना लेते हर बार अरे भाई तुम तो करता है स्ट्रीम चालू है ब्रो हाँ चल ही रहा है बट उसको भी म्यूट किया मैं लाइव लाइव कौन सा भाई सर लाइव क्या लाइव है लाइव चैट कैसे हेलो 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 3678 we see the Zener diode functionality. Okay, so Zener and avalanche diode are used in a voltage regulation, and they regulate the load voltage against variation in the load current or input voltage. Okay, so they are used in these applications cause the breakdown region large change and diode. Okay, large change and voltage. The voltage across the load resistance same as the general voltage. Okay, so CT is equal to KV by VR. So okay, constant. Okay, varactor diode. So what is varactor diode used for the variable voltage capacitor. Varactor diode is used known as the so it is known as the variable voltage capacitors. So they are also referred to the varicap and variable voltage capacitors or tunnel diode. The mode of the operation depend on the transition capacitance exist at the PN junction, where PN junction when the diode is in a reverse bias. The junction capacitor are discussed in detail. Okay, as shown in the figure. Reverse voltage as the reverse voltage increases further, the rate of change in the capacitor in the voltage decreases. The reactors are normally operated in the reverse voltage of 20 to 30. Okay, the symbol of the vector diode is like that. So tunnel diode has the heavily doped PN and region with about 100 to 1000 times dopant concentration, and then the typically semiconductor. Okay, heavy doping result in the narrowing in the depletion region, and the width of the depletion region of the tunnel is around less than the typical semiconductor. Because of the narrowing the depletion region, the charge carrier instead climbing of the potential barrier and pierce through the potential barrier, resulting in a tunneling of the carrier both in forward and reverse condition. Hence, the rendering in the diode bidirectional conduction property. In forward direction, the current reaches to the maximum IP at voltage is equal to VP at the referred peak voltage. Beyond the peak point, the current start decrease with the increase in the voltage as there are no carrier available for the tunneling, and the current reach approaches zero in forward voltage 0.4 to 0.5, but in PN junction effect starts, and the PN junction diode add a current due to the tunneling effect, and the current decreases beyond the peak till the point is a valley point, and the reason where the peak point and the valley point has a negative resistance characteristic. Voltage decreases with the increasing voltage decreases increase in the increase in current. Okay, at the valley point the slope of vi is di by dv is equal to 0. Okay, beyond the valley point the current start increasing and increasing in voltage, and the current reaches to the ip. Okay, so we can see that at the valley point as the current start increasing, negative resistance region in which current voltage increasing, current decreasing. Okay, as the current increasing voltage also increasing, but in the region in which current voltage increasing, current decreasing, so negative resistance region, there is no extra things allowed for the running. So after Schottky diode is known hot carrier diode have a metal semiconductor junction instead of the semiconductor diode. So metal junction, so is normally n-type silicon are used for the semiconductor where the metal are used. So a Schottky is a metal semiconductor diode in which we use metal instead of the semiconductor. So aluminum, platinum, and tungsten. Extra different construction of technique render these potential cutup and Schottky diode are the majority carrier conduction in both metal and semiconductor. The electron are the majority carriers, and the circuit symbol as equivalent to the majority carrier, in which symbol is this one. Okay, So shortcut diode is a highly efficient rectifier and which is essential in application such as switch mode, power supplies. Point contact diode and the power diode. So the diode are intended primarily and the point contact diodes, power diodes. Okay. So as we know, the light emitting diodes, photodiodes, applications photodiodes and circuits. So we know all the applications and this one. So when we find the cutoff wavelength is equal to, so okay, in next chapter, in next session we have tried to cover the BJT